Hi, I'm Gaurav. I will present our paper Hard QBFs for Merge Resolution. This is joint work with Olaf, Joshua, Meena, and Thomas. So, if I ask the question, is this formula satisfiable, or or the question whether this formula is true, so they are essentially the same question. Okay, so propositional formulas are a special case of QBF formulas, and satisfiability of propositional formulas is a special case of the, the of the problem of deciding whether a QBF formula is true or false. Okay, so the answer to this question is that yeah, the formula is satisfiable or true. So setting x to 0 and y to 1 shows that. So now we have another formula in which the second variable is a universal variable. So is this formula true? So it is easy to see that this formula is false, because irrespective of what x is set, you can set you can choose a value for u which makes some clause false. So in short, the value for u is given by u equal to x. What about this formula? Again, this formula is also false, because as you can see, irrespective of what x and y are set, we can always set u to some value which makes some clause false. The assignment that makes some the assignment to u which makes some clause false is x or y, and this can be written as a function. Okay, and this function is called a counter model for the formula. Now we have another formula. Is this formula true or false? Here the u variable comes before the x variable. So first thing to notice is that the function fu is equal to x is not a counter model for this formula, because um, for so the value, because the value of the universal variable can only depend on the existential variables to the left of u, so which is not the case here. So in fact, this formula does not have a counter model, and this formula is true. So coming back to propositional formulas, if we have to prove that a propositional formula is false, how would we do that? So one way is by giving the truth table, the entire truth table, but that would be of exponential size. Is there a more efficient way? So yeah, there is a way you could provide a proof. So you could start with a formula, and then you could start with your given formula, and you could derive new formulas out of it using some rule, and finally arrive at contradiction, and from that you could conclude that your given formula was false. So now there are many formats in which such a proof can be written. So this this is specified by a proof system. So in here we will focus on a proof system for propositional CNF formulas, which is called the resolution. So what it says is that if you have two clauses x or a and not x or b, you can derive a or b. So let's look at an example. So here in this example, the gray rectangles, they are clauses of your input formula, and using them you are deriving new clauses. So for example, from this clause and from this clause you can derive this clause, and you can proceed until you uh, obtain the empty clause, and from this you can conclude that your original formula was false. So there are special cases or restrictions of resolution. So the first one is tree-like resolution. So this uh, this uh, uh, this puts the condition that the tree that the this refutation graph should be look like a tree. Okay. The second restriction puts the condition that on any route to leaf path, no variable should be used as pivot more than once. So pivot is the variable being which was being cancelled. So for example, in this rule here, x is the pivot. Okay. So on any route to leaf path, no variable should be used as pivot more than once. So how large can these refutations be? So in the worst case, they can be of exponential size. So and so why do we study resolution? So because many SAT solvers are based on resolution, therefore exponential lower bounds for resolution, exponential size lower bounds for resolution give exponential uh, running time lower bounds for these SAT solvers. So this tells us something about the performance of the SAT solvers. So now let's go to QBF formulas. So all the best set solvers are based on resolution. So because of this, resolution has been adapted into many QBF proof systems. Okay. LDQRS is one such system, but the problem with LDQRS is that it blocks some sound inferences. So what this means is that there are situations where it's okay to derive a clause, okay, using two clauses, you could derive a third clause. It would not create an error, but uh, LDQRS doesn't because of how the rule of the LDQRS is specified. LDQRS does not allow this particular derivation. Okay, so uh, MRES was proposed in 2019 to remove this limitation. The paper that introduced MRES, it showed some strengths of MRES. Okay, so what it showed is that there are some formulas which which require exponential size proofs in other QBF proof systems, are but have short or polynomial size proofs in MRES. Okay, so these formulas are hard for other QBF proof systems but easy for MRES. Okay, so this is what that paper showed. In the current paper, we show some weaknesses of MRES. So we show that there are formulas which are easy for other QBF proof systems but hard for MRES. So before proceeding, let me first define what MRES is, merge resolution is, but that I will define with using some examples. So this is the formula that we have already seen. So the first thing that we do is we do some pre-processing. So we separate out the existential and universal variables. So after the pre-processing, so every line of the proof will have two things. One will be a clause over existential variables, and one will be a function specifying what value you should set the universal variable to. Okay, and the property that will hold would be that this U would be kind of a partial counter model. So in the sense that if you are promised that your existential assignment falsifies the existential clause, then if you set the universal variable according to the function given in the line, then that would ensure that at least the one of the input clauses is false. So we do this pre-processing, and so same pre-processing we okay, so we do this pre-processing and then we have this refutation. So so let's see what happens. So we have this x or y, x or not y. So this is same as resolution. Y is cancelled and we get x. Here we have not x or y, not x or not y, and gets cancelled and we get not x. Okay, if we look at the function part, so from u equals to 0, u is equal to 1, we get u equals to y. So y was cancelled from from the clause part, it comes into the function part. So it's easy to verify that the that the property holds that u is equal to y is a partial counter model for the existential clause x. So same thing happens after this, and finally what we get is empty clause and the full counter model. So we recall that the counter model for this formula was x XOR y, and this is what we obtain. So now, uh, so if the universal variable comes first, then what we will have is we'll have u equal to 0 here, u equal to 1 here. In this case, resolution will not be allowed. Okay, because the universal variable is to the left of x, and so there is a conflict. We cannot set u to x. Okay. Now, uh, the third example, in this example, even though the universal variable is to the left of the existential variable, but in both the both left and right, uh, we have u equals to 0, so this resolution is allowed. In this example, what we have is that the second clause does not have universal variable u. So the in the pre-processing of this x bar clause would give you x bar comma u equals to star. U equals to star means set u to anything. So again, now this resolution is not blocked because of u equal to star. So now let's look at uh, the relation between different QBF proof systems. So this is the picture prior to our work. Okay. So what was known was, so I'll just mention the relation between these three systems, okay, and the other systems. Okay. So what was known was that there are formulas which are easy for MRES but hard for other systems like these two systems. So mm, this was known. It was known that there are formulas which are easy for MRES but regular MRES but hard for these systems, easy for tree like MRES but hard for these systems, these five systems. Okay. So now what we do is we prove that there are formulas which are easy for which are hard for MRES and easy for these systems, formulas which are hard for tree like MRES but easy for these five systems. There are formulas which are hard for regular MRES and easy for these four systems. So what this shows is that this shows this shows some incompatibilities. Okay, so MRES is incomparable with these two systems. Tree like MRES is incomparable with these five systems, and regular MRES is incomparable with these four systems. Okay, so before I proceed, I want to mention something. So in QBF proof complexity, what we are interested in lower bounds using genuine QBF formulas. We are not interested in propositional hardness. Okay, so since all these systems for propositional formulas, they are they reduce to resolution. Okay, so if some propositional formula is hard for resolution, the same formula would be hard for all these systems also. But this is not what we these type of lower bounds are not what we are interested in QBF proof complexity. So these type of lower bounds belong to propositional proof complexity, so they don't tell us much about the QBF proof systems. Okay, so so all the lower bounds in this paper are uh, are uh, are using QBF, are using genuine QBF formulas. Okay. Okay. So now now let's proceed. So now I will give a proof sketch of one of the lower bounds. Okay. So the lower bound is the is for regular MRES. So I we prove that there are formulas which are hard for regular MRES. Okay, so now let me define the formulas. So these are called Q parity formulas. So they have a quantifier prefix. Okay, so they have this existential X variables, universal variable U, and existential variables T1 to Tn. So and they have the clausal forms of the following things. So x1 XOR t1. So in clausal form, this will be two clauses. So this thing will be four clauses. This thing will be two clauses. Okay. So this formula is false. So and the counter model for this formula is x1 XOR so on up to xn. So it is not difficult to check that this is a counter model for this formula. Okay. So the thing is that these Q parity formulas, they are easy for MRES. So we cannot hope to prove lower bounds for these formulas. Okay. So what we do is we use slightly tweaked versions of these formulas, which are called LQ parity formulas. They are also have also been well studied in literature. So how these are obtained is so we create two copies of these clauses, okay. And now what we do is, so the first clause we or with you, the second clause is we or with you are, these ones we or with you, and these ones with you are. So what we get is the clausal form of these things. Okay, so this formula is also false, and the same counter model uh, works for these formulas also. So now let me give the proof. So suppose you have a regular MRES refutation of LQ parity formulas. So this is your refutation. On the top you have axioms. Sorry. On the bottom you have empty clause and the counter model for LQ parity formulas. Now let's look at the at the part at the bottom of the proof, which in which the clause parts don't have any t variables. Okay, so for example, this last line, this the clause part is empty, it does not have t variables. So there may be other clauses, other lines, other nodes above this, which also in which also the clause part does not have t variables. Okay, so that would be this yellow region, and this is the boundary of this region. Now, so the proof has two steps. So the first step is we will show that for all nodes on the boundary, the clause part is wide. Okay, so it has a lot of literals. And the second step is, from the first step, we will conclude that the boundary is large. So it has a lot of nodes. So if wide means linear, then large would mean exponential. Okay, so now let me do the second step first. So assuming that the first thing is true, first that boundary clauses are wide, let me prove that boundary is large. Okay, so sorry. So let's focus on the part of the proof below the boundary. Okay, so the yellow part. Okay, now in this part, so each node has a clause part and a function part. So let's just delete the function parts. Okay, so now notice that what is left is just is just a resolution refutation. Okay, and from this, what we can conclude is that the clauses on the boundary, they form an unsatisfiable CNF formula. Okay, and from this, what we can conclude is, since the boundary clauses are wide, the boundary has to be large. Okay, so this is very easy to prove. So, like, okay. So now, so this finishes the second step. S- This finishes the second step here. Now let me do the first step. So now what we have to prove is that the boundary clauses are wide. So now let's look at this node at the boundary. So it has the clause part is C1 or C2 and the function part is F3. So this is derived using two nodes, this and this. So the is easy to see that the resolution at this point, the pivot of the resolution should be a t variable. So let's call it tk. Okay. So now let me also write the LQ parity formulas here so we can easily refer to them. Okay. So now what we can prove is that this first node tk or c1 comma f1, okay, this can be this will be derived using phi 1 to phi k. Okay, these things phi 1 to phi k, and this the second thing would be derived uh, using the clauses phi k plus 1 to phi n plus 1. Okay, from this what we can conclude is that the function f1 depends only on variables x1 to xk, because the clauses in phi 1 to phi k only contain the only x variables they contain are x1 to xk. Similarly for f2. Okay, so now since the resolution is on the pivot of the resolution is a t variable which is to the right of u, which is to the right of u, so therefore both the functions f1 and f2 have to be the same function. Okay, but since they depend on disjoint variable sets, so the only possibility is that they are constant functions, and from this we can conclude that even f3, so f3 will be equal to f1 and f2, and so f3 is also a constant function. And from this it is not hard to conclude that c1 and c2 should contain all the x variables, and therefore c1 or c2 is wide. Okay, so this completes the proof. So I will now conclude. So let's wrap up. So what we proved is we proved lower bounds for MRES and its restrictions, which are tree-like and regular MRES. From this, we got some incompatibilities with some other QBF proof systems. Then what is still left is, so we still don't know the relation of MRES with some other QBF proof systems. In particular, the relation with LDQRS is also unknown, and this is like unfortunate because MRES was mm, MRES was proposed as proposed to circumvent the limitations of LDQS. So mm, we should we would want to prove a relation between these two systems, but we still don't have that. Okay, so that's all. So thank you for your attention.